Hi everyone, how are you doing? I hope everyone is doing good. So welcome to another video of molecular basis of inheritance. In this video, we are going to cover how the DNA is compact and packed in the prokaryotic cell and eukaryotic cell. Okay, in the previous video, we have covered that DNA is the genetic material, how Griffith, Avery McLeod and McCarthy and Hershey and Chase they did various experiments to find out that okay, DNA is the actual molecule, actual substance which is transferred from one organism to the another, and this is the genetic material out of the various candidates like protein, RNA. Okay, so DNA was is the genetic material. Now we move to the next part of the chapter to understand how such a long DNA, okay, how such a long DNA fits inside a very small cell, even a bacterial cell or a eukaryotic cell. So it has to be what? How this long DNA can be accommodated in such a small nucleus? It has to undergo coiling and condensation and supercoiling. Just like imagine you have when you make a sweater, so the wool is there. When you open the wool, the thread of the wool, when you open it out, it is so long, it is in meters, but when you wrap it around and then it becomes a very small ball of a wool. So similar concept over here, that it has to be condensed, coiled and supercoiled to fit inside such a small nucleus. So we'll begin with the DNA packaging in eukaryotes. Approximately the DNA is 2.2 meters in a cell, in any cell. Okay, 2.2 meters, and it has to fit inside how much big cell? The cell is 10 raised to minus 6. The cell is, what is the size of the cell? 10 raised to minus 6. So this 2 meter, approximately 2 meter DNA has to fit inside this small nucleus of the cell. So it will undergo coiling, twisting, packing, and then it will become a small structure, and then it will be fixed inside the nucleus of the cell. Okay, so how does it happens in a prokaryotic setup? In a prokaryotes, as you are already aware that you have the cell, the cytoplasm is there. There is no definite organelles or definite compartments, and the nucleus is just nucleoid, we call it in this case. It is just suspended into the cytoplasm. In eukaryotes, you have a well-defined nuclei, well-defined organelles, etc., etc. So in prokaryotes, you do not have well-organized nucleus. No nuclear membrane is there, no nucleole is there. So the nucleoid is, the genetic material is actually the nucleoid, which is small and circular in nature. The prokaryotic chromosome is circular in nature and it is highly folded, and because we now know that the DNA is very long, approximately meters, it has to undergo folding. Okay, and it has to fix into that small bacterial cell. Okay, it's a naked ring of DNA, which is in bacteria. It is approximately 100 meters. 1100 meters long. I will just check with this the dimension. Okay, I think this is microns, 1100 microns, not meters. 1100 microns. I will check and I will get back to you on this. So let's begin with the diagrammatic structure of the DNA coiling in a bacterial cell. Which bacteria we're taking into consideration? We're taking E. coli. Okay, so circular DNA. So this is the first step. We begin with this. Okay, so circular, this is unfolded state. So the approximate size is 350 microns. Okay, 350 micrometers. Now this will undergo folding. So this circular DNA now undergoes folding. Okay. So now this falls into, now this will fold. So now the size is reduced. From 350 microns, the size is approximately 30 microns. Folded chromosome approximately 40 to 50 loops. Next step, next level of folding. So in between, RNA will serve as a rubber band, which will cause this loop to, come together and be held at one place. Next level of folding. Now these petals, okay, of the flower-like appearance, now they will undergo twisting and coiling themselves. You can see in this. Now the size is reduced more, 2 micrometers. Now from 350, they became 30. Now they became 2. So now this is super coiled folded chromosome. Okay. This is very tightly folded, so there will be some certain cuts created for certain regions of the DNA to be relaxed, and then it will be further fitted into the, and this is how the nucleus will be there in the cytoplasm of the E. coli bacterial cell. Okay. So there will be some cutting, that is nicking taking place, partially uncoiled chromosome. So this, 2-3 loops will be freed. Okay, and here also, or either in this form. So either like this or this form. So this is how the final chromosome, circular chromosome, which started from 350 micrometers, will end up in the size of 2 micrometers. So very, it has undergone a lot of coiling and super coiling and folding, and then the size is reduced, and now this can be fitted into a small bacterial cell. This is just this is in a short topic regarding the packaging in the prokaryotic cell structure. Next, we move on to the eukaryotic packaging. Okay, eukaryotic packaging is also very interesting. So you begin with the DNA, double helical structure. Bacteria, the structure of the simplified DNA is circular. In eukaryotes, it is double helical. So this double helical, as you can see, they go around. You can see these beads, which are proteins. Around that beads, they, bound around themselves, and then those again are wound around, and then again they go supercoiling, twisting and turning, and then it gives rise to this structure, and then this is fitted into the nucleus. Okay, so a eukaryotic chromosome is approximately 50% proteins. Okay, it is having 50% proteins in it. Because as you see in the picture, this coiling and supercoiling will require certain support, certain substance, okay, around which it can be wound out. So eukaryotic chromosome consists of chromatin, which is DNA plus proteins. Chromatin is nothing but DNA plus protein. So DNA is only the nucleotide structure, and you require certain proteins for the whole chromatin to be formed, which makes up the chromosome. So DNA plus protein is chromatin. We all know human cell consists of at least 2 meters of DNA, and this DNA is packed into 5 millimeters in diameter. Okay, so how the packaging takes place? So the first level of packaging is in the nucleosome structure. Very simple to understand. As you can see in the diagram, you have 8 balls of protein molecules. This is protein, this is protein, this is protein. It is known as histone molecules. Okay, histone protein molecules. So these 8 balls, 8 small structures, they come together, make one ball, and then the DNA wraps around this ball. And this DNA and the protein histone molecules, they are known as nucleosome structure. Okay, it's like a bead on string structure. Okay, just like you have the necklace wherein you have the chain, then you have the bead, then you have the chain. So certain amount of DNA will be used free, then again wrapping. Then certain stretch of the DNA will be used free, then again one bead. Okay, it's like this. One nucleosome, then DNA, one nucleosome, DNA, one nucleosome, DNA, linker DNA, one nucleosome, linker DNA, one nucleosome, linker DNA, one nucleosome, linker DNA. Okay, and around this nucleosome, you have DNA wrapped. Okay, so this is the DNA. This is also a DNA. Then you have DNA wrapped here, you have DNA wrapped here, you have DNA wrapped here. So when you open it, it is such a long structure. But when you do this wrapping and then you let loose some string free, then you wrap it again, another ball of histones, then some loose string, you just leave it. Then again you wrap it around some, another ball of histone protein. So like bead on string model. Okay, so histones are basically nothing but these are protein structures which will help in wrapping around the DNA. So these are small proteins responsible for coiling DNA into nucleosome. So naming is given H2A, H2B, H3 and H4, 2 of each. 2 of each. Okay, so this makes 8, total 8. 2 of H2A, 2 of H2B, 2 of H3 and 2 of H4. You can see 2H4, 2H3, 2H2 B in the front and 2H2O. Okay, so this makes 8 molecules of histone, which is known as octamer. This is the inner core of the nucleosome, and around this the DNA will wrap. Okay, so each bead is called a nucleosome. This structure is a nucleosome. This structure is a nucleosome. That is histone proteins wrapped with the DNA around itself. This is a nucleosome. Approximately the size is 10 nanometer. Okay, it is 10 nanometers, which covers 146 base pairs of DNA. It covers how many base pairs of DNA? 146 base pairs of DNA. Understood? So this is nucleotide bead on, this nucleotide will represent a bead and it is having dairy wrapped around itself. This middle portion, which is let loose, this is the linker DNA. Okay, so this is like, the diagram which I was drawing in the previous slide. So you have like a necklace. Okay, like this. This is what is represented over here. You have the DNA, you have the 8 octamer histone molecules around which the DNA is wrapped, linker DNA. Then you have again another nucleosome, another nucleosome. Okay, and in between you will see H1, another histone protein separately, which will act as a linker protein. Okay, so linker histone, H1 protein is known as linker histone. Nucleosomes are joined by linker DNA. So one nucleosome joined to another, this joined to another, this joined to another. They are joined by this linker stretch of DNA, which is held together by a linker protein, that is H1 histone protein molecule. Okay, so it connects one particle to the another, and approximately 200 base pairs are present in one stretch. Okay, they are loosely associated with DNA. Histone 1 are responsible for packing of nucleosome in 30 nanometer fiber. So now we will see this H1, which will bring about another level of packing. Okay, so as you see in the diagram, so the bead on string model, now it will again undergo twisting and coiling. Okay, now okay. So now the next level of packaging is the solenoid structure, wherein the H1 histone molecule will bring the beads more close to one another, more close to one another. Okay, so that is the solenoid structure. So nucleosomal bead is further coiled to form a structure known as solenoid. Okay, as you can see in this diagrammatic representation. So it has 6 nucleotides per turn. So the nucleotide, 6 nucleosome, not nucleotide, 6 nucleosome will come together and it will bound around themselves. Okay, with the help of the H1 protein. Like you can see it over here. Now they are coming more close. Earlier they were very far apart. You have, I'll just draw it and just show you. For example, you had this stretch of linker DNA, then one nucleosome, then one nucleosome, then one nucleosome, then one nucleosome, like this. So it was looking like a very loose necklace. Now this structure will take a more definite pattern of folding. So now it will come together. Let's say with it in this much area, how many nucleosomes are covered? 5. So this 3, 4, 6, let's say one more. So now this will come together. So 1, 2, 3, 4. Okay. Then you have 5, and then you have 6. So imagine this long necklace you folded, and you did turns, and you made it into such a small size. Okay. So this is how a solenoid structure will look like. Now, so earlier it was covering this much area, it took this much space. Now it is taking only this much space. Okay. So now the level is 30 nanometers. Understood? So 6 nucleosomes will come together and will make up a solenoid structure. Then next level of packaging is the chromatin level of packing. Okay, the diameter at this stage is 30 nanometer. Now, giving you a recap. So we began with a double DNA helix, which is 2 nanometers in diameter. Then bead-on string, that is the nucleosome, and then the DNA wrapped around linker DNA. This is approximately 10 nanometers, 11 nanometers. Now, when they again come together, supercoiling, I just showed you this. This is the 30 nanometer stage. The diameter is 30 nanometer. Now, they will undergo looping, okay, supercoiling, folding. Section of the chromosome is an extended form. At this level, the diameter will be 30 nanometers. Further supercoiling, and this is, then it takes the phase, it looks like a metaphase chromosome. Okay. So you can go from down to up or up to down. Then the solenoid is further coiled to produce a chromatin fiber, which is from 30 nanometer diameter. It becomes 300 nanometer diameter, and then it moves to form a chromatid, which is approximately 700 nanometer. So DNA level, bead-on string level, chromatin, chromatin fiber, chromatid, and then finally the chromosome. Okay, and ultimately 1400 nanometer diameter ka chromosome will result. Okay, we'll do a recap quickly again. So let's begin. We will open. We'll just open, and we'll go in the reverse direction this time for better understanding. Imagine this is your chromosome, which is this much diameter, 1400 nanometer in diameter. When you consider only this part of the chromosome, it will give you, when you open that structure, it will give you chromatid structure, condensed metaphase chromosome section having 700 nanometer. When you open this much part of that chromatid, then you see something like this. Okay, folded part structure. When you open this much part, you see like this bead-on string part. When you open this much part of the DNA, it looks like this. And when you just consider this much part, this is the double helical structure. And when you pack, so the coiling, supercoiling, twisting, turning, all this results into the final chromosome structure. So this is the microscopic picture of the packaging. This is the 2 nanometer in diameter wala structure, 30 nanometer. Then nucleosome. This is how a microscopic picture of bead-on string model looks like. And this is the folding, and this is how a chromatid looks like under a microscope. Okay, these are just microscopic pictures that I've included just for visual effect. And then last small 2 lines, euchromatin and heterochromatin region. This we have discussed in the earlier topic as well, I mean earlier chapters. Just for a brief recap, that this chromosome will have certain active regions, which will be known as eukaryotic region and euchromatin region, and certain inactive regions of the DNA, which will be known as heterochromatin regions. So euchromatin have a loose structure. They are active sites of genes. Heterochromatin, they have dense, dark structures. They are inactive site of transcription, means inactive genes over here and active genes over here. So euchromatin and heterochromatin. This we had discussed in the previous chapter in some of the videos. So there also we have covered this. So under the microscope, euchromatin looks lightly stained and heterochromatin looks darkly stained. Here you can see chromatin light state, dark regions are heterochromatin of the chromosomes. So that's all for this video. Now we will meet in the next video wherein we'll cover DNA replication and semi-conservative model of DNA. Thank you. Bye bye. Take care. Bye bye.